Okay, so this is our third and last sort of review of what we already know about acids and bases. And this is really that pH scale and our second learning objective in this Unit 8. So the pH scale is the most common scale that we use in order to classify compounds as acids and bases. The formula is this guy right here, the negative log of the hydrogen ion, but we also know that that could be H3O plus. Those two things are obviously interchangeable. And the table 16.1 just helps us to look at, you know, an acidic solution would have an H plus greater than 1.0 times 10 to the negative 7, because that's halfway between 0 and 1.00 times 10 to the negative 14. And we have the, so that means the OH minus would be less than that, and that means its pH is less than 7. Neutral is a pH of 7. This is all at 25 degrees Celsius, and basic is above 7. pHs can actually be negative. That's something we don't really go into because we won't come across really any solutions that will be like that, but they can. So if we look at this table right here, this chart right here, we can look at how pH and hydrogen ion concentration and hydroxide ion concentration relate to each other. And we're also introducing a new idea here called POH. So when you have that like P, you think of it as like almost an operation. So POH is just the negative log of OH minus. We're going to learn pKa, which is the negative log of the Ka. pKw, the negative log of Kw. It's, that P, and then what comes after it is the negative log of that. POH is just another scale to determine acidity or basicity. The POH is just the opposite. That 7 and down instead of acidic is going to be basic, and 7 or above is acidic. And it really helps us to do these calculations rather quickly using these two formulas down here, that the pH plus the POH equals 14, and that the concentration of the hydroxide and hydrogen ion equals that Kw, 1.00 times 10 to the negative 14. So we're going to use those two formulas to do a whole bunch of calculations here. So sample of lemon juice is 3.8 times 10 to the negative 4. What's the pH? So pH is, of course, the negative log of the hydrogen ion concentration. So the negative log of 3.8 times 10 to the negative 4. Plug that in our calculator, and we get 3.42. Let's take a moment here and talk about significant figures. So significant figures with pH has never been on the test. Significant figures play a very small role on the AP exam, but you don't want to lose a point because of something silly like significant figures. Significant figures with pH is tricky because it's really a logarithm. And then remember that, like, with scientific notation, since this is really a multiplication, then we'd really be adding the logarithms together. And when you add logarithms, it's the number of, or when you add, it's the number of numbers past the decimal point. So you just look at the total number of significance figures here, right? So the number that went in, the concentration, had 2 significant figures. Therefore, the pH has 2 digits past the decimal point. Like I said, it's not going to be on the AP exam, but that doesn't mean I'm not going to teach it to you. So that's the correct way to do it. A commonly available window cleaner, I think this is Windex, has an OH minus of 1.9 times 10 to the negative 6. What is the pH? So there's many different ways to get around this. We have those two formulas. In my opinion, the easiest way to do this is, the first thing is to find the POH, right? That's going to be the negative log of the OH minus concentration. So with the negative log of 1.9 times 10 to the negative 6, this equals 5.72. And then in your calculator, right, I can write the formula down. pH plus POH equals 14. So in your calculator, you just do 14 minus answer and get that the pH is equal to 8.28. Again, two significant figures, 2 digits past the decimal point. And then check, you know these rules. So if this number is greater than 1.0 times 10 to the negative 7, then it must be a basic solution. So what's the pH? Oh, it's greater than 7. That makes sense. We got 2 more questions. A freshly pressed apple juice has a pOH of 10.24. Calculate the H plus. Again, I think using that pH plus pOH equals 14 and then doing sort of the hard math. So right away, just getting, well, that means that the pH is 3.76. Now, the negative log of the H plus is equal to the pH. Remember, like, I know logs are no one's favorite, but you have learned this. Or you can just like learn the shortcut. Remember, a log without a base is really log base 10. So think about this as 10 down there. And then you would do 10 to the negative pH equals the concentration of the H plus. And if you are not savvy with logarithms, just memorize this formula. Plug it in. So this would be 10 to the negative 3.76. And what does that equal? 1.7 times 10 to the negative 4 molarity. 2 digits past the decimal point means my molarity has 2 significant figures. And the next question, a solution at 25 degrees Celsius. So they will often tell us it's 25 degrees Celsius as a reminder that we can use that KW. Has a pOH of 10.53, which of the following statements are true. So what I do in my head is, okay, a pOH of 10.53, that equals a pH of 3.47. So it's an acid. So the solution is acidic. Yes. The pH of the solution is 14 minus that. Yes. For the solution, the OH minus, there should be an exponent here. For the solution, the OH minus is 10 to the negative 10.53. So just as we have this formula over here, right? So the I should just say the OH minus concentration equals 10 to the negative pOH, right? So that would also be true. So that means all 3 statements are true. So how do we measure pH? So the easiest way to measure pH is with a pH electrode. It works on how much electricity is going through. You usually do have to standardize it, which means sort of you need to put the electrode in a standard, a solution that we know is pH. Usually we do 4, and then one that we know is pH 10, and sort of tell the sensor this is a 4, this is a 10, and then put it in the solution you want. And you can see, in this case, the milk with magnesia. Milk with magnesia is a saturated solution of MgOH2. And we can see the pH is 10.52. So that would make sense. It's a weak base. There's its pH. Or another way is to use an indicator. Those pH electrodes, although most of the time we think that an electronic measurement is better, they're hard to calibrate. They go out of calibration real quickly. I would really only necessarily trust maybe the first digit. I don't know if I'd really trust that second digit. An indicator is also sort of iffy, but it can definitely tell you acid versus base. And we did this, we did previously an acid-base titration where we used phenolphthalein. Phenolphthalein is an acid-base indicator. It is clear in an acidic solution and is pink in a basic solution. You can see it doesn't change at 7. It changes a little bit closer to like 9 or so. But when you're doing a titration, the pH changes so quickly that that change makes no difference. We'll see that a little later on. So these are some common indicators and their colors. You don't need to know. They will tell you the color change. Phenolphthalein is a good one to know. So we have a couple questions here that are just really, talking about, with 16.5, so strong acids and bases. The deal with strong acids and bases, or what, why is this? We've already done strong acids and bases. Is if this is a strong acid, then if this is the molarity of the solution, I know that this is also the molarity of the H plus. So the H plus is 0.040. So finding the pH of that solution is real easy, right? pH equals the negative log of the H plus, 0.040 molarity, which is 1.40, right? 2 digits past the decimal point because it's 2 significant figures in my concentration. And the reason why we can, what makes this so sort of special is because I know that since it is a strong acid, that whatever concentration the acid is, the H plus will be the exact same concentration. That's what's different about weak acids, is that if I had 0.040 molar HF, the H plus concentration will be nowhere near that. And that calculation is more like those ice charts that we did last chapter, and that's the new stuff that we will learn next. The next question, what's the pH of a 0.028 molar NaOH solution? So I know that if that's an NaOH solution, this is the concentration of the OH minus. And usually how I do this is find the POH and then do 14 minus that. It's just easier than doing, I could use concentration of OH minus times the concentration of H plus equals that KW 1.00 times 10 to the negative 14, but no need. So I would just do negative log of 0.028. I get a POH of 1.55 and then a pH of 12.45. And then, is this correct? Like, does this make sense? Yeah, we're talking about a strong base. Its pH should be pretty close to 14. We're getting right up there. A little bit trickier is the sometimes they're called diabasic bases. So they have 2 hydroxides, and losing both of those hydroxides is 100%. So what do I mean by that? Okay, if I'm talking about this calcium hydroxide here, and then full arrow, what does it dissociate into? Of course, it dissociates into the calcium ion and 2 hydroxide ions, and that's key. So if I have this molarity, calcium hydroxide, 0.0011 molar, Ca parentheses OH2, I need to remember that for every 1 mole of CaOH2, I will produce 2 moles of OH minus. This is me like showing you the stoichiometry, the dimensional analysis in, when you're doing this on a test, you just look at it and go, ooh, okay, multiply by 2. So I know this is going to be 0.0022. It will be the molarity of the OH minus, and then take the negative log of that. So the POH is 2.657. And the pH will be 11.34. Again, does that make sense? Yeah, it's a strong base. Its pH should be pretty high. This is the end of the beginning videos. So up to this point, we have done all these practice problems. Just where we're going next is basically taking everything that we learned about acid bases and everything that we learned about equilibrium and then putting them together. Which will be fun.